There we go. Now I'm recording, so everything I just said was a little bonus information for those who were here today. It wasn't actually relevant to the course. It was just some sort of trivia. So don't worry about it if the fact that I didn't record it is not actually a problem. Okay, so. Oh, I can stop sharing that, get that out of your way. Sorry, that poll was probably still on your screen, but now it's gone. So this is Calc 1. Let's get rid of Calc 1. So I want to then pivot to the lesson now. Just got to rearrange some things on my screen. All right. So section 3.2, which is what we're in right now. It's all about integrals involving trig functions. And we're going to go through some of this kind of in an organized fashion, right? One of the things we look at in this section is integrals of powers of sine and cosine. Okay. Let's go through what we know. Let's do it with sine. Here's an easy one, right? If it's just sine to the power 1, then we just get negative cosine. You guys yesterday, or 2 days ago rather, were working on sine squared, right? And we went over this one. This is the sort of thing where you can solve this by applying a power reducing formula. And a few steps later, just doing that power reducing formula puts it into a format that you can handle. The first term is going to be just a half, so we're going to get a 1/2 x in our antiderivative. And the second term, you've got that cosine of 2x, which you can integrate with a u substitution. So what we end up with there is minus 1/4 sine of 2x via a u substitution there. Okay. So the main point I want to focus on here is the strategy employed, right? With the first one, it was a nice simple sine antiderivative. With the second one, we had to use a trig identity to get there. Now, for sine cubed, we've done this one as well. We don't actually need to use a trig identity on this one. Or, well, we do, but it's not the same one. For this one, what I explained is you can kind of break this into sine squared times sine, right? And then replace sine squared with 1 minus cosine squared via the Pythagorean identity. Okay, so I'm just going to sort of label the moments where we use a trig identity. Okay. So that sine squared gets replaced with 1 minus cosine squared. And then now the result can be solved by u substitution. We say u equals cosine of x, and then we can solve that one. So do you want me to go through this one in a little more detail? I think I already went over this one, which is why I left a ... because we talked about that. I believe I went over this one as well, but do you want me to do it again, or are we okay? Here's a great question. Both of these, so yeah, these two, Wes asks a question, why are they different? Well, I mean, good question, because they're both equal to sine squared, right? In both cases, we're replacing sine squared with something, but we're replacing sine squared with a different thing in each case, right? So looking back in our trig identities, the Pythagorean identity here allows us to replace sine squared with 1 minus cosine squared. But the power reducing identity can allow us to replace sine squared with 1 minus cosine 2x all over 2. Why would we choose to use one or the other? Well, the answer to why we choose that is based on the context. What else do we have? In the first integral, we just have sine squared by itself. If we replace this with 1 minus cosine squared over here, then we'd just be integrating 1 minus cosine squared, and we kind of wouldn't have made any significant progress, because then the question would just be, well, how do you integrate cosine squared, right? If we're trying to integrate sine squared and you just flip it to integrating cosine squared, that's not any easier, right? So instead, we use that power reducing identity here because it takes us from a square of a trig function down to just a trig function. That's why it's called power reducing, right? It goes from 2 down to 1. And that's useful because then we can integrate that cosine function using just a simple u substitution. On the other hand, over here, replacing it with 1 minus cosine squared is valuable because then we since we have this sine of x like attached to it, available to us to use, then a u substitution with u equals cosine will work out because du require, du is going to use up that sine of x that we have. Does that kind of make sense? So it's context driven. If we had done this with the power reducing formula, then it would have been, I don't think it would have worked out so well, because then it's like, well, now what are you going to do with that sine of x, right? If you put this thing in here, then now it's like, yeah, I can integrate that, and I have this sine of x, and it gets much messier. Whereas this u sub works out nice and cleanly. So I will go ahead and fill in what we have here. So what we end up with is an integral, after the u substitution, we get 1 minus u squared. That's from this here. We have a negative sign in here, so I've got to stick that in there. And then the sine x dx get used up to make my du. So we have that, which I guess I can apply that negative sign by just flipping the order of that subtraction. Okay, so we end up here. Integrating this can then just be done with the inverse power rule. We have a third u cubed minus u plus c, and then undoing our substitution, 1/3 cosine cubed minus cosine plus c, and that's our antiderivative. Okay, now the sine squared and the sine cubed cases are like typical strategies, which can then be extended to solve higher power, like integrals of higher powers of sine. So suppose we had sine to the power 4. Pause. Question. Good question. For this one right here, is this a u or an x? Is that what you mean? Yes. Okay, it should be a u, as I've written. And the reason for that is because we converted this integral from a dx integral to a du integral. So the antiderivative that we are doing in this, step right here, this is a du antiderivative. So when we're checking this antiderivative, if we just check this step, we would want to be differentiating with respect to u and expect to get u squared minus 1. Does that make sense? Now, maybe you might want to sort of check what we've done. You might want to check it by doing a derivative. So if you take this answer and do a derivative, we should get like 2 cosine squared and then plus sine. And I think you'll find that, well, maybe we should do it. Maybe we should double check it. Let's double check our work before we do this one. So check it. I'm just going to, I'm going to omit the plus c when I'm checking my work because we know the derivative of c is going to be 0. So I'm just going to differentiate the rest of that here. Here we'll use our chain rule. We have a third times 3 cosine squared. So that's just the power rule. Then we multiply by the derivative of cosine, which is negative sine, right? Then we subtract the derivative of cosine, which is, again, negative sine. So it's going to be a plus sine. Okay. So the 1/3 and the 3 cancel out. We have cosine squared times negative sine and then plus sine. Rewriting that, it's like that. So then we can see that there is a sine of x here, here, and here. We can factor that out. And what's left is a negative cosine squared plus 1, or in other words, 1 minus cosine squared. And then, 1 minus cosine squared is equal to sine squared. And we have sine times sine squared, which is sine cubed. Amazing. This sort of thing is like we're getting the techniques we're using pull us so far away from the original intent of an integral, right? Which is find a function whose derivative is the thing you started with, like finding an antiderivative, that it can be hard to believe that you have the right answer because it seems so abstract, right? But yeah, I mean, it's always good to pause and actually check. Because, you know, the work, checking can be, you know, reversing it, right? This can be a lot of work, but it is satisfying to see that, oh yes, I do in fact have a valid antiderivative of sine cubed now. So looking at the chat, Isa makes a comment about distributing sine x first before integrating. Is that, you mean in this step here? Let's see. Yeah, we could probably do that. Then you'd be integrating sine by itself, which we can do. And then the second term would be integrating cosine squared times sine. For that second term, you'd still want to use a u substitution. So it would be similar. You'd still end up doing the same thing. It's just you'd have to break it into the two terms. So yeah, I mean, you could do that. You should get the same result. Oops, sorry. It's not intentional. Yeah, so yeah, we basically have two strategies we're seeing here, and the two strategies are, one, you can use a power reducing formula to simplify something, and the other is you can use the Pythagorean identity, right? So these two possible trig identities can help us with higher powers as well. So let's look at sine to the fourth. There is a question here about the negative sign. We're doing derivative of cosine is negative sine. This here is from the chain rule. This is there was already a negative, so this became a positive. I think that's what you're asking about, Salma. Is that right? Chain rule. Yeah, there we go. Cool. All right. Sine to the fourth. So any ideas? How do you think we can do sine to the fourth applying one of these two strategies? We're not going to do the whole thing. I think it might not be worth going through the entire process. We'll see. We'll kind of get it started. Yeah, so we want to split it into two sine squareds. Maybe not 2 times sine squared. I don't think that's what you meant. But basically sine squared times itself, right? Like 2 sine squareds multiplied together. Yeah. If we do that, then we can apply that power reducing formula again to each of them. So each of those sine squareds is going to be 1 minus cosine of 2x all over 2. 1 minus cosine of 2x all over 2. Now, then, multiplying these together, I guess 2 times 2 in the denominator is going to be 1/4. I'm just going to go ahead and pull that 1/4 out into the front of the integral. So now I have to do 1 minus cosine of 2x times 1 minus cosine of 2x. What do I have in there? Well, I have 1 times 1. I basically have to FOIL this, right? 1 times 1. 1 times negative cosine 2x, negative cosine 2x times 1. So those are going to add together. We got 2 cosines of 2x. And then negative cosine 2x times itself. So plus cosine squared of 2x, right? All that. Now, looking through here, what can I integrate? How am I going to be able to integrate that? Integrating 1 is easy. It's just a constant. So I'm just going to put a check mark by that to indicate that, like, you know, we can do that one. Integrating cosine of 2x here, you can use like a u equals 2x, a quick little u substitution to do that one. So that should be pretty easy. But how do we integrate cosine squared? That's not quite ready to integrate yet. Let's put a question mark next to that one. Thoughts on that? How do you think we would do cosine squared? Let's look at our trig identities. It is a 2x inside there, which is interesting. Velma suggests half angle. Maybe you meant double angle. A cosine of 2x is can be written in terms of you know, sine squareds and cosine squareds. But I think the 2x is not so much the problem, right? Like the fact that there's a 2x in there is kind of fine. That's not such a big deal because we can handle that 2x like we did in the previous case with a u equals 2x if we need to. The bigger problem is being squared. And our approach is really just the same as how we do it with sine squared, which is to use our power reducing formulas, which might have been what you meant, Thelma, because power reducing and half angle are very similar. They're like sort of just slight rearrangements of each other. But yeah, so there is a power reducing formula for cosine squared as well. And it's almost the same. It's just got where this has a minus, this one has a plus. Otherwise, they're identical. So we can do one more power reducing formula right there. It's still going to be doubling whatever the original input was. So this is one place where it's a little tricky because this time our input here is 2x. So when we apply the formula, what used to be x is now 2x. So 2x over on this side of the formula becomes 4x. Okay? So what we get when we apply that formula is 1 plus cosine of 4x all over 2. And now we can easily integrate this, the 1/2 term, here's another constant, and then cosine of 4x with a u equals 4x. So it's about applying trig identities until you get down to something that you can integrate fairly easily with a substitution. So I'll put a ... at the end of this one because there's a couple more steps to it, but you know, it's basically just do the integral of each term and you get a bunch of things added together. So that's you can imagine it would be a similar process if you wanted to integrate something like sine to the power 6. You would have sine squared, sine squared, sine squared, right? And each of those sine squareds would be you'd apply a power reducing formula, multiply that out, and then you'd have some cosines. You'd have like cosine squareds or cosine cubes even, but then you can integrate those with other methods, you know, like using either another power reducing formula or something else. the point is, you take higher powers and you write it in terms of lower powers, and that kind of gives you a strategy to integrate it. Okay, it feels almost recursive, right? Writing complicated things in terms of slightly less complicated things, and then if you can always do that, then you can always integrate everything. Okay. So that's even powers. If you have other higher odd powers of sine, you can use a similar strategy to what we did on sine cubed. So real quick, I'll sort of show you an example of that with sine to the power 5. You can say, okay, this is sine squared, sine. Okay, 2, 2, and 1. There we go. And then each of those sine squareds, this time, instead of power reducing, we do Pythagorean, 1 minus cosine squared. 1 minus cosine squared. Sine x. And then multiplying all this jazz out, okay, you get like 1 minus 2 cosine squared plus cosine to the power 4. And don't worry, you don't need to do any messy, power reducing things on this, because we have this sine x over on the side. And that sine x it makes this actually significantly easier, because it gives us access to the u substitution, u equals cosine x with du negative sine x dx, right? So this becomes negative integral of 1 minus 2u squared plus u to the 4th du. And that, of course, we can obviously integrate that pretty easily, because it's just a polynomial, right? So I'll put a ... on the end of that one as well. Then u sub. Yep, that's our key there. So this is a pretty high level discussion of the strategies to integrate powers of sine, but the same strategies can be used to integrate powers of cosine. Okay, so powers of cosine are very similar. You still have access to a power reducing formula, and you can still use the Pythagorean cosine squared equals 1 minus sine squared to do really the same exact stuff. Okay, and extending these strategies, you can integrate any power of sine or cosine. So that is the first thing that this section really goes over. Export. Okay. So then another thing is, what if you have like powers of sine and cosine multiplied together? That's another thing that we've been seeing a lot here. So stuff like sine x cosine x. This is not too bad, because you can just do like u equals one of them, and it doesn't. You can kind of do either one. Like you can do u equals sine, du equals cosine dx, and then turn this into u du, which is a half u squared, and then you get a half sine squared x plus c, right? So if it's something like that, and you could take a very similar strategy if instead of just sine times cosine, it was like, say, sine to the power 5 times cosine. Or honestly, just sine to the power like anything, sine to the power 100. Let's just illustrate the point by taking something kind of ridiculous. All right, sine to the power 100 times cosine. You can still use the same approach. U equals sine of x, du equals cosine x dx. And then we have u to the power 100 times du. And it's just 1 over 101, u to the 101 plus c. And we got our antiderivative. See how that works? So if you have some, and similarly, okay, if you flip this around, if you had like just one sine x, just one of those, and then like cosine to the power 27 or whatever, you can use a similar approach, but u equals cosine. Du would then be negative sine x dx. And you got a really similar situation here, right? Because this is just negative integral of u to the power 27, and then the sine x dx all goes into the du. And you got a similar 1 over 28, u to the 28. But it's with cosine this time. So there we go. Where it gets a little bit harder is if you have like if both of them are raised to a power. Okay, so for example, do two slightly harder examples. The first, what if you had sine squared times cosine cubed? Now, how do you approach that? Well, if one of them is odd, then you have a really nice way to do this. Okay, if you have one of the two powers on sine or cosine is odd, then you can say, if it's odd, I can peel off one of them, right? And then have an even number left over. So let's write that. Sine squared times cosine squared, and then one copy of cosine. Okay, if one of them is odd, you can do this. And then having a single cosine x dx with an even power left over means that we can keep the cosine, but then take the even power of cosine and put it in terms of sine. So we're then setting ourselves up. We're preparing to do a u equals sine x du equals cosine x dx, right? So that this cosine x dx on the end can be du. We just got to get the entire rest of the integrand, all of this stuff, we just got to get that in terms of sine. Since this was odd, what's left over is, after you take one on the side, is even, and we can just take pairs of two, cosine squared, however many copies of cosine squared go into that even number, and each copy of cosine squared can be replaced by 1 minus sine squared with the Pythagorean identity. So this would end up being, replace the cosine squared with 1 minus sine squared, and now the entire thing, this part here is my du, and then sine is going to be u, sine is going to be u, right? So this will become u squared times 1 minus u squared du. And that's just a polynomial, u squared minus u to the fourth. So once you've got it, once you've done a u substitution and got it to be a polynomial, it's easy. It's a breeze from there, right? So yeah, this strategy works. That strategy works whenever at least one of the two powers on sine and cosine is odd. Okay, even if they're both odd, you just pick one or the other and do this, just like demonstrated here, and you'll be able to then say, like, let's put the entire integrand in terms of sine, except for this one copy of cosine, this one cosine factor on the end, which we're going to use for the du. Do a u substitution, and then suddenly, ta-da, it's a polynomial. Integrate the polynomial. The tricky part comes when you have like they're both even, like a sine squared and a cosine squared. If you have both of them even, then you kind of just have to do the power reducing thing again. So in this case, you can do 1 minus cosine 2x all over 2 times 1 plus cosine 2x all over 2. We're just power reducing again. and multiplying that out, we get a fourth again, and then we have 1. Since this is minus and this is plus, we actually have some canceling of terms in the middle there. We just get 1 minus cosine squared 2x. And here again, we're just going to need to power reduce again. So so this now gives you the power. I mean, with these strategies, you can integrate any product of powers of sines and cosines. Just using these two trig identities. Either you're going to be doing the U substitution with the Pythagorean identity, or you're going to be doing a bunch of power reducing until you get something you can handle with, again, a U substitution, but more like a U equals a multiple of x, 2x or 4x or whatever, depending how many power reducing you had to do. So this is kind of the hardest it gets for powers of sines and cosines. There is also a similar approach to doing this sort of thing with tangents and secants. So I'm not going to go over that because it's really kind of like I said, it's a similar sort of thing. Oops, sorry, didn't mean to zoom in there. So I'll leave it up to you to take a look at that. Some of it is in the homework. You might see it show up on an exercise set or a quiz sometime. Maybe not a quiz, but certainly an exercise set, perhaps. We're talking about 3.2. The latter half of 3.2 is going through a similar kind of exploration of powers of secant and tangent. Now, so I'll just show you where I was going to pull this over and just show you. So integrating products and powers of tangent and secant here. Very similar approach. There's a couple things that you would need to do this. Like one of them in particular is the integral of secant. The integral of tangent is something that we studied back in Calc 1, but the integral of secant is not. At least I didn't address that one back in Calc 1. However, I have put it into a document for you. So going back into my lecture boards from yesterday, after class yesterday, I finally figured out the secant cubed problem. So here's secant cubed, everybody. It's actually in the textbook. It's an example in the section. So like we could have just looked it up, but you know, it was more fun to go through and try a bunch of things and mess it up and that sort of thing. So what you actually end up having to do here is you apply the Pythagorean identity right down here, but after you've already done integration by parts once. So these are both tools that I tried using. I just didn't put the tools together in quite the right way, right? So you do one integration by parts, then you replace tangent squared with secant squared minus 1, and this entire thing ends up in terms of secant. Now, this results in another copy of secant cubed, and you can use that strategy where you combine them together to get 2 of them, and you just divide by 2, right? So that's kind of neat. But the only thing left over then is a single integral of secant of x. So now you just need to know the integral of secant. So I go over how to do that right here. This is a very, the strategy for integrating secant is very bizarre. You had to multiply by secant plus tangent in both the numerator and denominator. And then you can finish it up with the U substitution. Not the kind of thing that's easy to come up with. That's why I put this comment. Who would ever think to do this? But yeah, it's kind of cool. But you end up with this lovely logarithm of secant plus tangent. Or maybe not lovely, maybe gross, depending on your perspective. So yeah, so that's a secant cubed. I won't go anymore. Suffice it to say, this section takes you, takes you deep into these strategies of using trig identities and integration by parts, use substitution, just all stuff we've already learned, but just applying it in these sort of messy trig problems. All right, that's as far as we'll go with that. So next week is next week, right? Yeah, because we're done for the because today's Friday. So next week we'll get into our next major topic, which is still going to involve trigonometry, but it's going to take the concept of use substitution that we've learned before, and it's going to flip it inside out in a very clever way called trigonometric substitution. So have a lovely weekend, everybody. I will see you on Tuesday. Monday is Martin Luther King Jr. Day, so that's why we don't have class.
I have one question.
Go ahead, Ali.
So if you have a problem with a power, but then it also has a thing in the inside of it, like a trig function, which do you do first?
Can you clarify what you mean?
Oh, so like if you have like a tangent to like the fifth power,
Oh,
and
yeah.
then you have something inside of the tangent like 2x,
Oh, sure.
what do you do with that?
So you basically would want to apply some strategy to handle the power of the trig function first.
Okay.
So start by doing these things I've been kind of showing you today, like where you're like with that case, you're probably going to peel off one copy of tangent, and then you have tangent squared times tangent squared times tangent, right? Because you said 5, right?
Yeah.
So 2 and 2 and 1. And then each of those tangent squares, you can use a Pythagorean identity to put it in terms of secant.
Okay.
And then I think from there you might be able to do something. So like I said, I didn't actually go over it with tangents and secants as much today. The strategies are slightly different, but you can look at the examples in the textbook, and you'll find some that are pretty similar to what you're talking about. Now, the fact that there's 2x on the inside, you can just handle that at the end.
Yeah,
You know
that was
what
my
I mean?
problem.
Yeah.
But so when you split up into tangent squared, and tangent, do you still keep a 2x in all of them?
Yeah, you would. Yeah.
Okay.
Mhm.
That was my question. Yeah.
Gotcha. The other thing I'll say, which might be helpful to you, because I think you might be, are you working on one of the ones on the exercise set?
Oh, yes.
Yeah. So the other thing is there are these other trigonometric identities, some of which are useful. And in particular, if you have 2x inside something, you have these double angle identities, which can potentially help you out. See them here?
Yeah.
So, also consider making one of those substitutions. It's very unique to the 2x case. If it were like 3x or whatever, then this wouldn't work so well, but that's an option too.
That's on D2O, eh?
That trig identity thing?
Yeah.
Yeah.
Okay. Thank you.
You're welcome.